All right, let's get started. So, welcome everyone to the Simons Institute. My name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute, and it's my great pleasure to invite you all to the boot camp of the program on data structures and optimization for fast algorithms. As you all, I'm sure, know, Simons Institute is a leading international venue for collaborative research in TCS and related areas. It was established in 2012 with a generous grant from the Simons Foundation, which continues to support us very generously. The Institute convenes the world's leading researchers in the theory of computing and related fields, as well as the next generation of outstanding young scholars. And the main programming here is thematic semester programs, but we also run a lot of workshops and summer clusters. And the Institute also engages in many outreach activities to popularize algorithmic thinking broadly in science, humanities, and engineering. So this week, we kick off the activities for this fall semester's program on data structures and fast algorithms for optimization with the boot camp. The boot camp, as always, is as intended to acquaint program participants with the key themes of the programs. It will consist of 5 days of tutorial presentations on a variety of topics related to the program from leading experts. And really sincere thanks to the organizers of the program, who are also the organizers of this boot camp. So, who are Alina Ain here, Monica Hensinger, Yintat Lee, Jelani Nelson, and Aaron Sidford. So maybe a round of applause for them. So as always, all talks here are live streamed on YouTube and are recorded for posting on the Simons website, where they enjoy a life and impact long after the bootcamp winds down. And in particular, I want to mention the bootcamp talks in particular have served as a really valuable resource for students and young researchers and anyone else trying to learn the field worldwide, to learn about the key results of a topic in a carefully curated form. So I know some of you, the speakers, are working hard. Some of you are speaking all day and so on, but rest assured that it's really worth the effort, because your talks will have a long life and be very worth it. And particularly for this topic, where progress has been happening at a frenetic pace with such remarkable breakthroughs, I think it's really we are all looking forward to the outcomes of this boot camp. So some logistical things before I hand over to Aaron. Food is provided before the first talk and during the breaks. For lunch, you're all on your own, but there are many options walking distance. And we ask that you please leave all food and drinks outside before you come into the auditorium, so it helps us keep the auditorium clean. And if you need to leave your stuff when you go for lunch or elsewhere, there are lockers in the back side of the room, which are very easy to use. And we have our videographer, Umayyad Far, who will help you with any AV issues during the talks. And so finally, I want to give a special round of thanks to Elizabeth Yuen, who was the events person organizing all the logistics for this week's event, and as well as this program going forward. Thanks, Elizabeth. And so now with that, I'll hand over things to Aaron, who will give a sort of a detailed welcome and intro to this program.
All right. Thank you very much for the introduction. Hello, everyone. Good morning. I am so glad you all made it here. I am really excited that this program is starting. As introduced, I am Aaron Sidford. I am one of the main organizers of the program, along with the rest of this team of organizers that Venkat just introduced. Before, you should have all probably been receiving many of you should have been receiving a welcome email from me. If you haven't already, please reach out. And before we get into all the tutorials for the day, what I wanted to do is take this talk to kind of introduce the program a bit more broadly. Before going into the more technical tutorial talks on each of the kind of main focuses of the program, I wanted to take some time here and talk about the motivations of the program, set the stage for all of these talks, and have you all have a sense of kind of what's bringing this program together and what we'll be doing for some of the things that we'll be doing for the next many months. So let's start at the beginning. Like, what is this program about? Why are we here? This is kind of a broad question. I know many of you are here for a number of different reasons, and there's a lot of different motivations to participate in the workshop. Whatever they are, just a quick thank you again to the Simons Institute for making this program possible and letting it happen. So what I want to talk about is maybe one sort of broad motivation for this program in particular, one thing that's motivating it happen. So I think there's a lot of particular reasons this program and workshop is rather timely. One of the many motivations for having it now, though, has to do with a certain suite of algorithmic advances that have happened over the last decade. So one of the key motivations for this program is over the last decade for a range of sort of fundamental, foundational optimization and algorithmic problems, things ranging from linear system solving to minimum cost flow to computing Gumry-Hu trees. And this is just a small sampling of the many advances that have happened over the last decade. And for many, many of these problems, there's been a number of advances in getting provably efficient algorithms. These faster algorithms in many cases have overcome decades-old barriers that have persisted for getting fast runtimes. And for many of these problems, not only were there advances showing you could solve these problems more efficiently, but in some of these cases was even shown that for these problems, you can solve them almost linear and near optimally, kind of nearly closing the door on a number of long lines of research, at least when it comes in terms of obtaining efficient runtimes. So this would be maybe enough for motivating having some sort of program to talk about all these sort of amazing advances and see how much further we can push them. But one of the key emphases in this program, and the way we decided to structure this program around these advances, has to do with the fact that many of these results not only share a commonality in terms of the types of tools and techniques that were brought to bear to ultimately achieve these advances. So to get these faster runtimes, interestingly, a number of these results, they were obtained by building upon and combining sort of a wide range of algorithmic tools. And the Simons Institute, which has been famous for its reputation over the last many years and bringing together researchers from a number of different areas, it seemed like having a program on tying these together even further was a nice idea. So you get a sense of this. Many of these advances, they build and combine a number of different algorithmic tools. So many of these results use a number of different optimization methods, things like multiplicative weights or interior point methods or gradient descent. They also used and built upon different sort of data structures. So things like dynamically maintaining decompositions of graphs known as expander decompositions, dynamically maintaining ways of solving certain sorts of linear systems, dynamically maintaining a vector undergoing certain types of implicit updates. And in addition, these results use a variety of different sketching techniques. So things like Johnson-Lindenstrauss, subspace embeddings, and count sketch, and many, many more. So these results have been using and building upon sort of a wide range of techniques. And to get a sense of how these techniques have been coming together to get these sort of improvements, there's a number of, I think, interesting ways that these results and more have kind of highlighted surprising connections between these different areas of research and different sort of problems that you might consider, maybe you wouldn't have traditionally considered in one of these areas, but make a lot of sense to consider when you consider them in sort of a broader algorithm that's using techniques for all of them. So there are many, many ways these different algorithmic tools have come together. Here's just one example of a kind of common way these different algorithmic tools have been used to get certain sorts of improvements. So here's one way that a number of these results have worked. They start at a very high level with a difficult optimization problem that's trying to be solved. Maybe solve a linear system, solve a linear program, commute a minimum cost flow in a graph. At a high level, if you look at some of these algorithms, what they're doing is applying some sort of optimization method to solve these difficult optimization problems. And what these optimization methods do is you can think of they follow some sort of iterative procedure that takes this complex problem that people have been trying to improve runtimes for decades, like minimum cost flow. And they essentially give a result saying you can solve that problem if you can solve a certain sequence of subproblems. Maybe solve a linear system, maybe multiply a matrix with a vector, maybe compute a tree in a graph. And one way that then these results have been achieving faster runtimes for solving these problems is by rather than just designing faster runtimes for solving sort of the individual problems, like a faster linear system solver or a faster matrix vector multiply, though some do that, they treat this entire sequence of subproblems that are being solved as a data structure problem. The question of being able to solve a sequence of linear systems, multiply a sequence of matrix vectors. And then to ultimately solve that data structure, they use certain sort of sketching or randomization or sampling techniques to speed up the solution to this data structure problem. And then by putting all of these pieces together, faster runtimes have been achieved. And this sort of broad template has been followed for a variety of different methods, from one term that I think Sushant might talk a bit more, like the Laplacian paradigm, solving certain graphical linear systems known as Laplacians. They apply certain iterative methods like Richardson iteration for solving the linear system, where the, certain decompositions are then either data structures or decompositions are used to make implementing the iterations cheap. And like ultimately computing some of the decompositions uses certain sorts of randomization. A variety of fast algorithms for linear programming, semi-definite programming, minimum cost flow. You can all kind of explain them in this broad template in terms of what optimization method is being used, what are the sequence of subproblems looking like, and what sort of optimization techniques do you need to solve the data structure problems. And what's I think been interesting about this template is it's led to a number of new optimization methods. If you're trying to design optimization methods to make the data structure problem simpler, that motivates new problems you might want to solve. So it's given new data structure problems you'd want to solve, new criterion for designing optimization method, and new sketching techniques you might want to develop to fit into this framework. It's also given rise to some interesting themes in sort of algorithm design. It's motivated wanting to have data structures that you can implement, even if like the next round of the input to the data structure depends on the previous. If you use these data structures in a loop, you need them to be able to succeed even if an adversary can see the output of the data structure in a previous round. And so this has made some new connections between areas. But this is just one example of how these different techniques have been combined together to get some of these algorithmic advances. Here's one other example that's been kind of fun. For certain problems like natural dynamic data structure problems, like computing a maximum matching in a bipartite graph, you can think of the natural dynamic problem of wanting to maintain a maximum matching in a graph under, let's say, edge deletion, so some sequence of modifications to the graph. And there's been recent work that says, well, you can use different results from optimization theory to reduce this dynamic problem to a sequence of static problems. So this optimization theory results, when analyzed carefully, they say if you can solve certain sorts of regularized versions of max matching or certain sort of regularized optimization problems, well, they have stability properties you can prove such that if you can solve just that sequence, they naturally are compatible for solving the dynamic problem more efficiently. In the particular case of maximum matching under a graph undergoing edge deletion, there's been work showing you can do this, and then in turn, this motivates new sorts of optimization or graphical optimization problems you want to solve, which in turn have been solved by the template on the previous slide of using different optimization methods, which are then implemented by solving a data structure problem using more random sampling. So this is just two quick examples of, I think, the very rich interplay that's happened between designing dynamic algorithms for graphs and for linear algebraic problems, designing new optimization methods, and building new sketching techniques towards getting different sorts of algorithmic results. All right, so with all that motivation aside, what's the actual goal for the program and how are we structuring things? So we have these three main focuses, sort of data structures, optimization, and sketching. And the use of all of these techniques to get more efficient, faster algorithms for solving foundational problems. So one of the goals is to study all of these things, to seek advances in each of these areas, design more efficient algorithms, build new tools and frameworks. But particular for emphasis for having this program at the Simons Institute, which I think does a fantastic job of bringing together researchers from many different areas, is to really explore the interplay between all these areas and look for new, robust, and interesting sort of connections between these different areas of research and kind of expand and enhance the research at all of these areas. So the goal of the program, beyond the sort of very, very broad goal of improving everything that falls in this category, which is rather big, is to sort of look for new opportunities for collaboration and research and progress at the boundaries of these different areas of algorithm design. So that's the very broad goal. How are we actually going to do this or structure the program? Well, the first step, as you all know, is we're going to have boot camp this week. So we'll have a workshop this week introducing sort of fundamental tools and techniques in all of these different areas. At the end of this week, we'll have a town hall to discuss how we actually want to structure the week-to-week of the program, what sort of seminars and reading groups and sort of weekly activities we want to have in this broad area of research. We'll then have a workshop on dynamic graph algorithms. We'll have a workshop on sketching, and we'll have a workshop on optimization. Right? So we'll have a workshop on each of these main areas, in light of the different sort of connections between them that we're exploring during the program. As for bootcamp itself, the plan for the week is to give a variety of talks that sort of give the fundamental tools and techniques in each of these areas, as well as some of the sort of common tools and languages and notation and things that might be helpful for doing research at the boundary of these different areas. So after this talk, we'll kick things off with Sushant talking about graph linear algebra. A common thing underlying a number, but not all of the results I mentioned, is a way of looking at different graph optimization problems in terms of linear algebra. And one of the things that's facilitated for a number of problems, bringing all of these different tools to bear, is this sort of linear algebraic view of these graphical problems. And since this is one of the many sort of foundational glues between these different areas of research in recent years, it's what we're going to start the program with. So that'll be Sushant presenting right after this. We're then going to continue with this afternoon. Thachapal will start talking about graph data structures, one of the main areas of the program. And then, since a lot of the program will be structured around getting faster algorithms for solving all of these problems and more efficient algorithms, as we know, not every runtime you might hope to achieve is always possible. And it's good to know what to do if you are trying to solve one of these problems for a while and are rather stuck. And building off the bootcamp that happened last week, we'll have some talks on conditional hardness and fine-grained complexity. So we all have some common tools and techniques of what to do should we not actually achieve faster algorithms or be a little stuck for any of these problems. We're then going to have a day of talks on sketching, followed by a number of different shorter talks on optimization. So we'll have a few lectures on first-order optimization methods, some talks on higher-order optimization methods. We'll also talk about matrix data structures that are a natural bridge of data structure and sort of sketching and linear algebra and some of these methods. And we'll end the workshop with some talks on interior point methods. The idea is when all this complete, we're not necessarily giving talks on the problems in the intersection, but we're giving all of these tools and techniques that are being combined in all of these different ways to get these results. So we all have some common, I think, terminology and shared experience in all of these methods for as we continue to talk together over the course of the program. Before I move on, thank you very much to all the presenters. I look forward to all your talks this week, and thank you very much for all volunteering. One thing before I wrap up and we take a quick break and then turn things over to Sushant is one thing I want to mention is this is all what I just presented is sort of the formal structure of the program that's in place for every single program. There's a sequence of workshops. There's a sequence of workshops starting with a bootcamp. In addition to that, there's some things that we're going to organize together over the course of the program. And this Friday at 11 a.m. here, we're going to have a town hall to discuss how we want to structure the week-to-week of the program, what things we want to facilitate, research and discussions and collaborations over the course of the program beyond these workshops. We have a lot of freedom here to coordinate different sorts of weekly seminars, whiteboard talks, social events, so we can discuss what we want. It's up to us what we want to do. I'm looking for volunteers to help organize social events, maybe organize a weekly seminar. The idea is over the next few days, I wanted to mention this right away so that we can all talk amongst ourselves over the next few days. Feel free to talk to me during breaks if you have any ideas, or please, if you'd like to volunteer for any of this. And I look forward to discussing with all of you. Also, just two administrative notes. There's a mailing list for the program. Should have received a welcome email from me if you're in the program. If you haven't, let me know. And Sushant kindly set up a Zulip we can use for collaborating over the course of the program. So just want to leave those links there. So that's it. Thank you all. I can pause for a moment for questions. We'll take a few minutes to stretch our legs, and then I'll turn it over to Sushant. So thank you. I know it's kind of early, and this is a kind of broad talk, but are there any questions?
If there are, I have the mic.
Oh, fantastic. All right, so let's take 5 minutes. If you want one more sip of coffee or a drink or something, we'll let Sushant set up. So come back here in 5 minutes for the first tutorial. Thanks.